Hello, welcome to today's lecture of scalable data science. Today we are continuing on our theme of finding nearest neighbors. Today's lecture is going to be on locality sensitive hashing. So, here was a question of finding near neighbors that we are looking at. We were given a set of data points, right, and we were free to pre-process these data points as we wanted. Given at query time, we would be given a query, one query point, and we would be asked to return the nearest data point to the query. Well, the nearest, or maybe some version of it, maybe the k nearest, or maybe we are given the query point along with a target radius, and we are being asked to return all the points in the data set that lie within this target radius, target distance to the query. Okay. These are all variants of the question that are important in one setting or the other. So, before we delve more into this, let us step back and talk a little bit about how we are representing an object, what is the distance and so on, right. Because when we dealt with KD trees, we kind of implicitly assumed that maybe there is a nice distance function like L2 that is available, and because typically KD trees work with some with Euclidean distance or versions of that. Right, and it needs a metric space in which you are sort of putting in points. The locality sensitive hash functions also have some restrictions, and we will see. We will sort of see what kind of distance functions are actually useful. Okay. So before we talk about distance functions, we need to talk about that what is a point. What is a point? Right. I mean, there is obvious representation of a point as a vector. Right. I mean, we represent images as vectors, we can represent documents as vectors, but there are also other representations. You could also think about a data point as really a set or a multiset, right. For instance, given a particular document, it is not a priori obvious to you if you have not thought about it, that what is the best representation for it. Should it be a word by position matrix? Right, when one axis is words, the rows are words, the columns are the columns are the positions, and then you create this matrix. Is that a useful representation? Should I represent it as a multiset of characters? Right, and it turns out that none of these two representations is actually a good representation. Right, it turns out that the nice representation for a document is in terms of there are few nice representations. One nice representation is as a set of words in the document, right. I mean, what is a word? Well, it is easy to define what a word is if you are writing in English, but if you are writing in a language in which you are not using space as a separator, there is no natural separator, it is not easy to define what a word is, right, and then we have to go to some other things that we see today. There are but once you do this, we will represent the document as a set, right. And these will be basically the two standard representations that we use, either a set or a vector, right, and either the vector will be normalized or it will not be, and the distance function that we use might differ in these two cases, might depend on whether the vector is normalized or not. So, let us go towards representing documents as sets. So, as I said that in most cases, in a lot of cases, you might be in a setting when you can't really rely on a natural separator for the documents, right. And one particularly useful technique that's used in let us say analyzing any documents, or in the web companies analyzing HTML pages, is in using shingles. So, what is a shingle? A shingle is nothing but a set of k consecutive characters that appear in the document, right. So, it does not make sense to take each individual character, because then every document would basically have the same representation, right, because the frequency of the characters is more or less the same in any large enough document. So what you do is you take k consecutive characters, right, and then that substring is a shingle. Okay. So, rather than store the substring, the list of this substring or the multiset of these substrings, what we do is that we hash each of these substrings into a 64-bit number, right, using something like MD5 or SHA, using something like MD5 or murmur3, any fast hash function would do. And then you store the multiset or the set of these shingles. For instance, here is a particular sentence, right? A sly fox jumped over the lazy hen. And you can create a shingle by sliding a window. Suppose you want to create a shingle of size 5, right. So, you want to size k equal to 5. So, you slide a window of size 5 over the document, right, which is only one sentence. So, the first shingle is A SLY, maybe the next shingle is SLYF, maybe the next shingle is LYFO space FO, and you keep on creating these shingles, and then you hash them, and then you store the list of these shingles. The idea is that keeping k consecutive characters preserves some amount of semantics of the document, and two documents that are similar according to some similarity measure that you can define on these two sets also have been shown to be semantically similar in terms of human judgment, right. So, what are we trying to do? We are trying to capture the semantic similarity, right, in terms of this some mathematical notion of similarity that will define on the sets of shingles, and shingles have turned out to be particularly useful representation in terms of doing this. Okay. So, now we have represented the document as a set. So, what do we do? So, here are two natural, so here is a natural similarity function over sets, right. It is called a u.a.r. similarity. You must have heard about this. What is this? It just says that if you have two sets A and B, if you have two sets A and B, and you want to calculate the u.a.r. similarity of these two sets, what you do is that you take the region, you take the number of elements in A intersection B, and then you divide by the cardinality of A union B, right. It is easy to see that this always gives you a number between 0 and 1, right. So, this is a notion of similarity. So, u.a.r. similarity of A with A would be 1, right, and if the two sets are completely disjoint, u.a.r. similarity would be 0. So, corresponding to this, we can define a notion of distance functions. u.a.r. distance, this is not as commonly referred to, but it is basically the same thing, and u.a.r. distance is 1 minus u.a.r. similarity, right. So, again, if we are talking about a metric, u.a.r. distance obeys all the properties of a metric. That is, u.a.r. distance of A with itself would be 0, u.a.r. distance of of A with B is the same as u.a.r. distance of B with A, and more importantly, it obeys triangle inequality. That is not so obvious to see actually for u.a.r. distance, but it does. And that is actually going to turn out to be fairly important. Suppose we have vectors, right. So, think about images. So, images are often represented as vectors. So, if it is a 64 by 64 image, you can represent one coordinate of the vector for each of these positions. So, the size of the vector is 64 cross 64, right, and then maybe you have the grayscale value of the image at that particular pixel as a value in that vector, right. Documents are also often represented as sets. You could convert documents are also often represented as vectors. You could convert the set into a 0 1 vector, the set that you have constructed, or you could create a vector with some TF IDF or some other weighting, right. Basically, the position, there is a word, there is a position for each shingle, or a position for each k-gram, or a position for each word, and then you sort of you put in some kind of weighting for that shingle, or for that k-gram, or for that word in that particular position, right. And once you create, once you represent as vectors, there are of course natural distance functions. There is the L2 distance function, there is some L1 distance function, other LP distance functions, if the vectors are normalized, that is if the vectors lie on let us say on the unit sphere, then one other useful distance function that sometimes used is the angle between them, right. And because the vectors are normalized, the angle between them is also satisfies triangle inequality and other properties that you need of a distance function. Okay. So now that we have a handle on the object representations as well as the distance function, let us talk about the possible solutions. Okay. Now, we have seen an excellent candidate for a possible solution, because if instead of near search, right, near duplicates, we are talking about exact duplicates. then we knew what to do. We would have used a hash table, right? And that would have been perfectly fine, because suppose here was a question that given a set of documents, given a query, you are asking, does this exactly same web page or the exactly same document appear in your data set? If you wanted to answer exactly same, then you could have created a MD5 hash of the entire document, and then you just index these, you just store these MD5 hashes in a hash table, right? And answering the query is fairly straightforward. So the question is now, can we adopt this hashing idea or the hash table idea to search for not exact match, but close enough match? Okay? This is what we will try to do here. So, and the clever idea by Indyk and Motwani, this is really sort of pioneered by Indyk and Motwani, and there have been a lot of huge line of literature in this line. The clever idea is to repurpose the idea of collision, right? Because remember what were we doing when we were designing hash tables? We were trying to avoid collisions, because collisions would lead to increase in the query time. But now collisions are exactly what you are looking for, right? What we want to do is that we want to repurpose collisions so that collisions now happen. Remember, in the designing hash table, collisions happened over x and y that are, arbitrary, right? Any x could have collided with any y. So now we repurpose collisions and say that, can I make, if x and y are similar, can I make them collide? Can I make them, can I have a greater chance that that if they are nearby, they go to the same hash bucket, and if they are far, they go to different hash buckets. Basically, this is really the idea. The fact that this is possible and the fact that this is possible efficiently, none of these are obvious questions, right? So here is what we want, right? We want to say that, supposing you have 2 points x and y that are close, but x is far from z and y is far from z. So maybe you want x and y to go to the same bucket, but you want z to go to a different bucket, right? Farther off points should fall in different buckets, and close enough and points that are nearby to each other should fall in the same bucket. Okay? This is what we want. So we need to define this a little more formally, and we'll sort of step through the definitions in sort of increasing order of formalism. But so here is one intuitive, slightly more concrete definition than before, right? So how are we choosing the hash functions? So this cannot be done. This cannot be done with deterministic hash functions. Instead, we'll again go to this idea of choosing hash functions randomly, and we'll say that, okay, the algorithm will design a hash family, right, that given a distance function d or a similarity measure s, right, the algorithm will sort of design a hash family, and then at runtime it will choose a single hash function from this family, right, and we will call this family to be locality sensitive if, right. Remember that the probability is over the random choice of the hash function. If over the choice of the hash function, the probability that for any two x and y, the probability that h of x and h of y are the same, right, is high if x is close to y. That if close to y, they have a higher probability of collision if they are over the choice of the hash function, and if x and y are far apart, the probability of collision is small, again over the choice of the hash function, right. See, very important to note that here the probability, here we are not talking about any randomness in the input, right. The input data is fixed, specifically the x and y are fixed, and this has to work for all x and y over the random choice of the hash function, right. And then it is not even clear that such functions exist, right, because how do I know? There are, as I said, there are many different similarity functions, we already saw a few, there are many different distance functions, and how do I even know that it is possible to create such families, right. For instance, if I were choosing the hash family H to be the set of all functions, right. Maybe the hash family, so here is a sample function, right. Maybe the hash family is the set of all functions that go from u to 0 to m minus 1, right. So, then this particular collision probability is independent of the distance. So, it certainly does not satisfy a locality sensitive property, right. So, how do I even know that such hash families exist? That is the first thing that we will see, that not only do such hash families exist, it is very easy to create, it is not very hard to create such hash families, and that is a clever trick, right. So, again, I mean, before we see this, let us try to define this a little more formally, right, and let us define this in terms of not the distance function, but in terms of similarity functions, although there is a one to one, there will be a one to one link between the two. So, and this was the definition given by Charikar in 2002. Given a universe U and a similarity function S, right. So, what is the similarity function? A similarity function is nothing but it takes a pair of elements and it returns the similarity of this pair, right. For instance, and you can assume that it satisfies some simple properties. For instance, it is the similarity of x with y is 1 if and only if x equal to y, right, and the similarity is a symmetric function. The similarity of x with y is the same as similarity of y with x, right. Let us say a similarity function is any function that satisfies the simple properties. Okay. So, given a universe U and a similarity function, right, does there exist a probability distribution, does there exist a hash family, and such that we can choose from this hash family according to probability distribution, right, such that we satisfy this, that the probability of collision is exactly equal to the similarity between x and y. The probability of collision of x and y is exactly equal to the similarity between x and y. Okay. This is what we call to be the first definition of locality sensitive hashing according to similarity preserving locality sensitive hashing. Okay. Now that we have asked this question, now that we have formalized it, now we can go back and ask that do such functions exist? Can I define? We have already seen some natural notions of similarity, let us say the Jaccard similarity. We will see a couple of others. Do functions exist for these natural notions of similarity? Okay. Let us take a simple one. Suppose my points are bit strings of length d, right. So, one natural notion of similarity or distance here is known as the Hamming distance. What is the Hamming distance? The Hamming distance is nothing but if you are given two strings of length d, Hamming distance between them is the number of positions in which they differ. For instance, I have written two strings of length 10 here, x and y, and the positions in which they differ are here, here, because here the 1 there is a 0, there is a 0, there is a 1, all of these are similar, and I think at this point, right. So, the Hamming distance between them is 3, right, because they differ in exactly 3 positions. You can also define a similarity, a Hamming similarity among them, that as 1 minus h of x y by d. So, this lies in 0 1, right, and it satisfies all the property of a similarity function. Right. The Hamming similarity between these two is 1 minus 3 by 10, which is 0.7. Okay. And if the Hamming similarity between x and x is 1, then that means that the 2 bit strings are exactly the same, okay, because they do not differ in any position. Okay. So, then here is the question, then does this similarity have a corresponding locality sensitive hash function? Okay. It turns out yes, very interestingly, right. Let us define this hash family. What we say is that the hash family really consists of, let us say we take all subsets of size s. So, there is an element of the family let us say that, okay, let us define it simply first. Let us say that there is an element of the family such that h I of x is equal to x I. Okay. So, right. So, the first family that I define is a very simple family of size d, right. What are the members of the family? There is exactly d hash functions, okay, and the dth hash function is nothing but it is something that picks up the ith coordinate, right. It is something that picks up the ith coordinate, right? Just one bit, 0 or 1. Okay. So, let us look at that first. Okay. Let us look at that first, then we will do the analysis for the larger d. Okay. So, what can we say? What we can say that if we pick h from h, what is the probability that h of x will equal h of y, right. It is not very hard to see that, okay, picking h, picking the hash function is really sort of deciding which coordinate we focus on, that we focus on one of the coordinates and we see that, okay, do x and y, are x and y the same in this coordinate or not, right. And therefore, this probability is exactly equal to the Hamming similarity between x and y, because that is exactly the fraction of the coordinates on which they are same. If they are same in 70% of the coordinates, then according to, if I pick a hash function from this family, the probability of them being the same will be exactly 70%. Okay. And so, this particular family satisfies exactly the same, satisfies the, is actually a locality sensitive hash family according to the definition that we gave, right. What we can do, what we often do is something a little different, right. What we do is to say that, okay, let us pick instead of a single coordinate, let us pick k coordinates, right. That supposing we are picking 3 coordinates, 1, 1, 5, 7, right, and we define a hash function out of these 3 coordinates. For instance, if I pick s to be 1, 5, 7, which is the position 1, 2, 3, 4, 5, position 5, position 7, right, and then we look at, for x we look at only the bits in positions 1, 5, 7, that gives us 1, 0, 0. For y we again look at positions 1, 5 and 7, that again gives me 1, 0, 0, right. Therefore, the hash function h s really is then the projection of the strings x and y onto this particular coordinates. Okay. Then you can ask the question that, okay, what is the probability that h of x equals h of y, right. And here now, because we have used k coordinates, the probability is now is h x y to the power k, right. Because we are choosing k coordinates, let us say we are choosing them we are choosing them with replacement, right. And so the probability, and so for any one coordinate, right, the probability that they are same is sh of x y. So, for k coordinates, the probability that all of them are similar across x and y is sh x y to the power k. Okay. So, we see that at least for a very simple distance or similarity function, we do have a notion of locality sensitive hashing. Let us go to more complicated functions. Okay. So, here is one that we have just mentioned. Supposing x and y are unit norm vectors, right, which means that they lie on the surface of the unit ball, right. So, they can lie in R D. So, x and y belong to R D. but because we are looking at only two vectors x and y, we might as well draw the ball in 2 dimensions. Okay. So, the distance between x and y is really the angle between them, the theta angle between them. Okay. So, the similarity between x and y would be defined as 1 minus theta by pi. So, I am assuming that cos inverse always returns a value between 0 and pi. So, therefore, this gives me a value between 0 and 1. Okay. So, this is the similarity, and this is the distance. So, here the distance is more natural to define than the similarity. So, let us now look at, so for this particular similarity function, right, is there a corresponding notion of locality sensitive hashing, and it turns out that there is, and it is a very clever one. It is a okay. What we do is this, we say that we choose, let me draw this first and then I'll explain. We choose a vector uniformly at random, right. We choose a vector uniformly at random, and then we say that take the dot product of this vector with x, right. Take the dot product of this vector with x and then see the sign of that, okay, and take that sign as the hash value. See, the sign is plus 1 or minus 1, right, or you can think of it as 0 and then 1 and then 0. Okay. I mean, basically it just gives you a single bit. So, but what is the sign? So, let us just look at it geometrically. So, if I take this blue vector, if I take the sign of x along sign of v dot x, it is really nothing but you take the hyperplane that is orthogonal to this vector v, right, and then you see which side of the hyperplane, the sign of v dot x tells you which side of the of this particular hyperplane x falls in, right. So, one side is the positive side, the other side is the negative side. Okay. So, now the question is that why does it satisfy, I want to claim that it satisfies this locality sensitive property, right. That is, I want to say that using the definition of the similarity between x and y, I want to say that the probability that h v of x equals h v of y is nothing but s x y, which is equal to 1 minus theta by pi. Why is that the case, right? And it is easy to sort of understand it from the geometry, because from the geometry you see that okay, when does the hyperplane, see, we can think of the hyperplane and the vector v are in one-to-one correspondence. So, I could as well think of choosing the hyperplane instead of choosing the vector v randomly. Okay. So, when does a hyperplane give you different signs for x and y? The hyperplane gives you exactly different signs for x and y when it passes through the hyperplane passes through the angle between x and y, right. That means that when the vector is chosen such that the corresponding hyperplane passes through this angle between x and y, at that point sign of v dot x is different from sign of v dot y. And what is the probability of that, right? The probability of that, well, I mean the probability of splitting is exactly theta by pi, because the hyperplane will be chosen, I mean because the angle will vary from 0 to pi, and therefore the probability of choosing this angle, right, the probability of splitting x and y will be when the hyperplane passes through that, and because it is uniform, the angle is chosen, the vector is chosen uniformly at random from the surface of the unit sphere, the probability of this is, the probability of splitting is exactly theta by pi, and therefore the probability of not splitting, that is the probability of collision, is exactly 1 minus theta by pi. Okay. So, is that okay? So then we also see that even for this angle distance there is a particular locality sensitive hash function, right. So, we seem to be pretty lucky in our choice of distance functions and so on. So, the question then is this luck going to sustain? So, before we go there, and that is what we will do in next class, let us just do a little bit of an aside for a minute about how to pick a vector, how to pick a direction uniformly at random, right, because that is not entirely clear. I mean I told you that you sample V as a uniform random direction in space, but how do we do this, right? And it is a very clever trick. So, and that is why we want to see this. That suppose we want to choose in d dimensions, we want to choose a vector x such that 2 norm of x is 1 and the direction of the vector is uniform among all possible directions in the in d dimensions, which means that it lies on the surface of the ball as d minus 1. This is known as the unit ball of radius d minus 1 of the unit ball in dimension d minus 1. Okay. So, here is the way to do this, right. What you do is that you take Gaussian distribution, you take n01, right, and then you make d independent samples from this. Call these x1 to xd. These are the values of the initial values of the d coordinates, okay, and then you normalize it with the length of the vector x. So, recall that the length of the vector is also a random variable, right, but you take x and then you divide by the you calculate the L2 norm of x. The L2 norm of x is as you know, it is summation xi square root, right, and then you normalize it. So, now you certainly have a unit norm vector, right. So, how do I know that it has a uniform direction in this sphere? So, for that what you need to do is that you need to write the equation of the d dimensional Gaussian in polar form, and what you will be able to see that because we are writing it in polar form, the r and the theta, the r which sort of is the captures the length and the theta which captures the direction, they can be treated independently. And because here we have effectively normalized by they can be treated as independent random variables, right, and here we have normalized it with the norm of the vector. So, the r effect goes away, what you are left with is a uniformly chosen direction, right, and this is again a useful exercise to perform that we will possibly also look at in our exercises that we give to you. Okay. So, with this aside, let us end today. What we saw is that we saw some initial definitions of locality sensitive hashing. We gave a slightly formal definition of it in terms of similarities. Then we were wondering whether such locality sensitive hash functions even exist, and at least for two of the similarity measures, two of the useful similarity measures, the Jacquard similarity as well as the angle based similarity, we did see that we are able to create using very clever, very simple sampling methods, locality sensitive hash family. Next, we will extend this to other kinds of similarity measures, and we will see how to create a hash table out of this locality sensitive hash measures, and that is it for today. Thank you.